Hello everyone, my name is Dr. Saeed. Today I will solve this fractional differential equation with variable coefficient by the method of power series. The equation is d by dx of 1 minus square root of x into y of x plus 1 and lambda times half Caputo fractional derivative of y of x with 0 initial condition and x lies between 0 and 1. Okay. For this method, we need to suppose our unknown function y of x in the form of an infinite series. So let's suppose that y of x can be written as summation from n 0 to infinity some constant cn and x to the power n by 2. Okay, in this equation, instead of taking x to the power n, I am taking x to the power n by 2 because of this function, which is the coefficient of y of x, and it has power x1 to the power 1 by 2. Taking clue from that power, I am taking the power x to the power n by 2 here. The rest of the process is the same. I will just plug the value of y of x into this equation. I will apply this Caputo fractional derivative on this function, and then I will arrange the series. I will compare the coefficients and I will get some recurrence relation, and I will find Cn. As soon as I will find Cn, I will plug it here and this will be the solution. Okay, now plug this one into the equation. This becomes d by dx into 1 minus square root of x into y of x, which has now this series representation, sum from n0 to infinity cn x to the power n by 2 and then 1 plus 1, and then I have lambda, which is any real number, and then I have Caputo fractional derivative from 0 to x of order 1 by 2 of y of x, which have the series representation, and from 0 to infinity cn x to the power n by 2 equal to 0. Okay, now I will differentiate it. It has two terms. I will apply product rule of differentiation. First, I will differentiate this term. The derivative of 1 is 0. So 0 minus the derivative of x square root is 1 over 2 times square root of x, and then this term will remain as it is, summation n from 0 to infinity cn x to the power n by 2 plus 1, then plus, then I will hold this term 1 minus square root of x, and then I will differentiate this series. Okay, it becomes summation cn and take power down n by 2 and x to the power n by 2 minus 1. Okay, here one need to be observed that since this series is starting from 0, but as soon as you differentiate it here, because of this factor n by 2, if you take n is equal to 0, this will make the first term 0, which is useless. So instead of starting from n0, I will start it from n1 to infinity, and the derivative of 1 is just 0, so it has only one term. So okay, now we have lambda, and then I will take this derivative inside the series, summation n from 0 to infinity cn, and then I will apply the definition of Caputo fractional derivative. The definition is this: d from 0 to x of order alpha of some function x to the power n is equal to gamma of n plus 1 over gamma of n minus alpha plus 1 into x to the power n minus alpha. This is the fractional derivative of x to the power n for alpha. So using this formula, here my alpha is half and n is actually n by 2, so it becomes gamma n by 2 plus 1, and in the denominator gamma n by 2 minus alpha, which is 1 by 2 and plus 1, and x to the power n by 2 minus alpha, which is 1 by 2 equal 0. Okay, now we need to simplify this. I will multiply this term to this series and I will join the power of x inside the series. So this becomes summation n from 0 to infinity, and here is minus 1 by 2 is coefficient, and then cn and then x to the power n by 2, and joining this power, which is negative 1 by 2, so it becomes n by 2 minus 1 by 2, and then minus, and then I will multiply this term to this 1, which becomes 1 over 2 x to the power minus 1 by 2, plus same, I will open this expression 1 times the series will remain series as it is, and from 1 to infinity cn n by 2 x to the power n by 2 minus 1, and then I will multiply square root of x to this series, and this becomes minus summation n from 1 to infinity cn n by 2 x to the power n by 2 minus 1, and this extra power 1 by 2, and then lambda summation n from 0 to infinity cn gamma of n plus 2 over 2, and in the denominator n by 2 and minus 1 by 2 plus 1 by 2, which is plus 1 by 2 x to the power n by 2 minus 1 by 2 equal to 0. Okay, here you can see that this is when combined n by 2 minus 1 by 2. So this is the same power as we have here, x to the power n by 2 minus half, and in the first series we have the same power, but in this series we have different power. Okay, first I need to make all the powers of x same, because only in that case I can take this term common. So since all the term except this term have different power of x, I need to change my index in such a way that the power of x will coincide with the remaining powers. For this I will replace n by n plus 1 only in this term, and everything else will remain as it is. So this becomes minus 1 by 2 summation n from 0 to infinity cn x to the power n by 2 minus 1 by 2 minus 1 by 2 x to the power minus 1 by 2, and series, and now n, when n is n plus 1, 1 cancels, so it starts from 0 to infinity, and cn, so it is cn plus 1, n by 2 becomes n plus 1 by 2, and x to the power n, when replacing n with n plus 1, this becomes n by 2, and one extra half come out will combine with negative 1, it becomes minus 1 by 2, and now you can see that the power of x is now same as the other terms have, and everything else will remain as it is. Okay, now we have made the powers of x in each term same, but now we have a different issue, and issue is this, that there is one series which is starting from 1, but other series are starting from 0. In order to combine all these series, I need to, all these series have the same starting point. So what I can do, I will open the series which are starting from 0 one term. So I will open one term here, so it will start now and 1, and I can open this again first term and also in the last series. So when I will take one term out of this series, the remaining series will be start from n is equal to 1. Okay, bringing this first minus 1 by 2 x to the power minus 1 by 2, and here minus 1 by 2, and when n is 0 this becomes c0 x to the power, when n is 0 x power only left minus 1 by 2. Okay, then the series will start from 1, I will write it at the end, and from here again I will take one term outside, so when n is 0 it becomes c1, and then it is 1 by 2, and then x to the power minus 1 by 2, And in this series, since it's already starting from 1, so no need to enter term take out. In the last series, again I have to take one term outside, so it becomes lambda, and it has c naught and gamma of when n is 0 it is 2 by 2, which is 1, so gamma 1 over gamma 1 by 2 and x to the power minus 1 by 2. And then every series now will start from 1, so I will combine the rest terms in a single series. So writing as plus series n from 1 to infinity into, okay, from first term I will take minus 1 by 2 and then cn, because x have the same power in all the series, so I will take that term common as well. Okay, in this series I will be left with cn plus 1 and then n plus 1 over 2, and this will be taken as common. In next series I have minus cn and n by 2, and in the last series I have lambda and then cn and then gamma of n plus 2 over 2 and whole over gamma of, and outside we have x to the power n by 2 minus 1 by 2 taken as common from all these 4 series and equal to 0. Okay, now I have given initial condition y is equal to y of 0 is equal to 0, and I have assumed that y of x as summation n0 to infinity cn x to the power n by 2. If I expand this series, I will left with c0 plus c1 x to the power 1 by 2 and then c2 x to the power 2 by 2 and then c3 x to the power 3 by 2 and plus so on. This is y of x. Using this condition, I will put x equal to 0 in this series, and since x is 0, all the term will become 0 except the first term, and since it has equal to 0, that means the value of c naught is 0. Okay, using this fact in this series, since c naught is 0, so this term is 0, and the last term, because it also contains c naught, this term is equal to 0. I am left with only first term and this term. Okay, in these two terms I have minus 1 by 2 and then minus 1 by 2 this is 0, minus 1 by 2 c1 and into x to the power minus 1 by 2, which is common. And I have this bigger series, which is summation n from 1 to infinity into, everything will remain as it is, and I can write 0 with x to the power minus 1 by 2 and 0 with x to the power n by 2 minus 1 by 2. Okay, now comparing the coefficients of, first compare the coefficient of x to the power negative 1 by 2, it becomes minus 1 by 2 minus 1 by 2 c1 is equal to, here it is 0, and then comparing the coefficients of x to the power n by 2 minus 1 by 2, we have here and we have here this coefficients, so it will becomes minus 1 by 2 cn plus cn plus 1 n plus 1 over 2 minus cn into n by 2 plus lambda cn gamma n plus 2 over 2 and gamma n plus 1 over 2 is equal to 0. Using this equation, I can find minus 1 by 2 is equal to 1 by 2 c1 sorry, here it is positive, this is positive, so this becomes negative 1 by 2, which means c1 is 1. c1 is 1, and now from the second, now I have c1 is equal to 1 and c naught is equal to 0. Okay, here I will take n plus 1 over 2 into cn plus 1, this term remain as it is, and out of that these 3 terms, I will take Sn common. Actually, I will take minus Sn common. So minus Sn common, here I am left with only 1 by 2. From this term I will left with plus n by 2, and the last term I will left lambda gamma n plus 2 over 2 whole over n plus 1 over 2 is equal to 0. Shifting this term on the right hand side, I am left with Cn plus 1, and dividing by this coefficient, it becomes now 2 over n plus 1 into Cn. Inside I can take LCM from first two terms, which is n plus 1 over 2 and lambda time gamma of n plus 2 over 2, and in the denominator gamma of n plus 1 over 2. Okay, now it becomes n plus 1 is equal to, shifting this factor inside, it will cancel out the first term, so Cn will remain outside. First term becomes 1 minus lambda and then 2 over n plus 1, and then gamma of n plus 2 over 2, and then gamma of n plus 1 over 2. Okay, now Cn plus 1 is equal to Cn and 1 minus lambda, and now I will write this factor as gamma of n plus 2 over 2 gamma of n plus 1 over 2, and I will write this because this is already in the, this factor n plus 1 is already in the denominator, so n plus 1, and I will write this 2 in the denominator of n plus 1, so like here. What is the use of this step? Here I have a formula, x time gamma x is equal to gamma of 1 plus x. Here you can see that the same term is outside of gamma, which is inside, so I can apply this property, and using this property it becomes Cn plus 1 is equal to Cn 1 minus lambda gamma of n plus 2 over 2, and this becomes gamma of 1 plus n plus 1 over 2, and one more step of simplification will lead us to Cn plus 1 is equal to Cn 1 minus lambda gamma n plus 2 over 2, and in the denominator gamma of n plus 3 over 2, where n will start from 1, 2, 3 so on, and I have C naught equal to 0 and C1 is equal to 1. This is our recurrence relation, but we need to find the value of Cn to get our solution. So I will expand this recurrence relation taking different values of n, starting from n is equal to 1. When n is 1, it becomes C2 equal to C1 into 1 minus lambda, and gamma of when n is 1 is 3 by 2, and in the denominator it is gamma 4 over 2, which is 2. Okay, since we know that gamma of 3 by 2 can be written as gamma of 1 plus 1 by 2, which is 1 by 2 gamma 1 by 2, and it is equal to 1 by 2 gamma square root of pi, and gamma of 2 it is equal to 1 factorial, which is 1. So this becomes C1 into 1 minus lambda 1 by 2 square root of pi, and over I have 1, and since the value of C1 is 1, so C2 is 1 minus lambda square root of pi over 2. Now taking n is equal to 2, this becomes C3 and then C2 into 1 minus lambda gamma of n plus 2, n is 2, so 2 plus 2 4 over 2, which is gamma of 2, and in the denominator it is 5 by 2, which can be written as C2 1 minus lambda gamma 2 is 1 factorial, which is 1, and gamma 5 by 2 can be written as gamma 1 plus 3 by 2, which is 3 by 2 into 1 by 2 into pi square root. Since gamma 5 by 2 is equal to gamma 1 plus 3 by 2, and this is using the property 3 by 2 gamma 3 by 2, and the value of 3 by 2 is here, so this becomes 3 over 2 into 1 over 2 and square root of pi. So this becomes C2 had this value, we have already found it, so plugging the value of C2, 1 minus lambda square root of pi over 2 into 1 minus lambda, and in the denominator we have 4, which can be written as the numerator 4 times 4 over 3 times square root of pi. Okay, taking one more n is equal to 3, and using the same concept I can write it 1 minus lambda times pi square root over 2 into 1 minus lambda times 4 over square root of pi, and then 1 minus lambda times 3 square root pi over 8. We have the value of C4 in this product, and we can find C5, C6, and we can guess the value of Cn. So continuing this way, Cn becomes 1 minus lambda pi square root over 2 into 1 minus lambda 4 over 3 times square root of pi into 1 minus lambda 3 times square root pi over 8, so on up to 1 minus lambda gamma of n minus 1 plus 2 over 2 over gamma of n minus 1 plus 3 over 2. Or using the infinite product, this can be written as Cn is equal to infinite product starting from k1 to n minus 1, 1 minus lambda gamma of k plus 2 over 2, and then gamma of k plus 3 over 2. This is the form of Cn. So using this Cn back into our assumed solution, which we have supposed that y is equal to summation n from 0 to infinity Cn x to the power n by 2. Since here we have already found that C0 is equal to 0 and C1 is equal to 1, so we need to expand this series up to 2 terms. So when n is 0 it becomes C0, and then when n is 1 it has C1 into x to the power 1 by 2, and then series from n starting from 2 to infinity Cn x to the power n by 2. Okay, first term is 0, second term is 1 times square root of x, and then summation n from 2 to infinity, the value of Cn, which is infinite product k from 1 to n minus 1, and then 1 minus lambda gamma of k plus 2 over 2 and denominator k plus 3 over 2 into x to the power n by 2. So which becomes y of x is equal to square root of x plus summation from n1 to infinity, n2 to infinity, and 2 to infinity is also 2. Infinite product k from 1 to n minus 1 into 1 minus lambda gamma of k plus 2 over 2 and gamma of k plus 3 over 2 into x to the power n by 2. This is the solution of our given variable coefficient fractional differential equation. Okay, here we see that for some special values of lambda, like for example lambda is equal to gamma of 2 over gamma 3 by 2. If we take this value and plug this value into this solution, we have some special kind of solution. Like if we expand this solution, y is equal to x, y of x is equal to x square root plus, if I expand this a little starting from n2, since n is 2, this becomes infinite product from k1 to n minus 1, since n is 2 it is 1, so this is k1 to 1, so this infinite product has only one term under this case, and then 1 minus lambda have this value plug here, and then this term remains here into x to the power n by n is 2, so 2 by 2 is 1, so x1 plus one more term when n is 3, this becomes infinite product from k1 to 2 because n minus 1, so when n is 3 is 2, 1 minus the value of lambda which I have assumed here, and then everything remain as it is. Okay, this becomes square root of x as it is, and expanding this infinite product which has only one term, plug k is 1, so 1 minus this remains as is, and when k is 1 becomes 1 plus 2 3 by 2 gamma 3 by 2, and in the denominator gamma 2 into x, and you can see that gamma 2 cancel out gamma 2 and gamma 3 by 2 cancel out gamma 3 by 2, so this is 1 minus 1 which is 0, so this term becomes 0. In the next term, since this term is also here in the next term, so this also becomes 0, and hence all the remaining terms will become 0, and this infinite series will now have a finite number of terms, and the solution will reduce to only y is equal to square root of x for this value of lambda. Similarly, if we take the value of lambda like this, gamma 5 by 2 over gamma 2, which can be simplified to 3 times square root pi over 4, this infinite solution will reduce to only two terms, which is y is equal to gamma x square root minus 1 minus 3 pi over 8 into x. So these special value of lambda will significantly reduce the infinite terms to just finite number of terms. So in this lecture I solved a fractional differential equation with variable coefficient by the method of power series method, and I obtained a solution with just elementary functions in series form. Thank you for watching.